All right, hi, it's Brian. We're going to look at proportion inference in StatPowers. I'm going to look at a couple different parts of the site. So we're going to look at first inference of one sample proportion. So imagine this scenario. I am interested in let's say I'm a researcher and I'm researching sea turtles in a certain area of the ocean. Sea turtles. Let's say I'm interested if the sea turtles, what proportion of sea turtles are like way less than 20 kilograms. So let's say 20 kilograms is a very low weight for sea turtles, for this specific species of sea turtle. So I'm interested in what proportion of sea turtles is less than 20 kilograms. Here I've got the data. I've actually got the weights of 55 sea turtles. So on StatPowers, if I wanted to look at estimating, creating a confidence interval, you go down to confidence intervals and you want to set the confidence level. Leave it at 95.95 for now, a 95% confidence interval. And now for under proportion estimation, expand that, and I'm going to say, I'm going to consider a success. Now this is a success is of course the technical statistical term for this. It's any turtle that has a weight less than 20 kilograms. So what I get now is a whole bunch of stuff. Notice that it summarizes for me. No, success. Success doesn't mean it's a good thing. It just means it's just the term that statisticians use. There was two sea turtles that were less than 20 kilograms out of the sample of 52. Sample proportion is p hat 0.038. Fair enough. That's just 2 divided by 52. Now we've got 4 different confidence intervals. Most textbooks teach you to approximate the distribution using a normal distribution. That's what the walled confidence interval is. And for walled, a 95% confidence interval for the proportion, the population proportion, is from negative 0.014 to 0.091. Actually, I can click on this to get a little chart of the confidence interval. If you like seeing it visually, this is 95% probability in the middle. The exact Klopper-Pearson confidence interval is a different. Let's see if I click on that, it should shrink down again. The Klopper-Pearson confidence interval is a little bit more precise. It's exact, but it uses a binomial random variable to model the sea turtles, and so it has the benefit of being it's exact, which is to say we're trying to find this is a picture with it uses an F distribution. The problem is some people think that it's too conservative, so it's like a little bit wider than it needs to be. There's a couple other methods, or maybe it's too narrow. I forget what the complaint is that people have. But there's a couple others. There's the Wilson score interval, and there's the Argesti-Cool confidence interval. I like the Argesti-Cool confidence interval. All they do to calculate that is you just add 2 successes and you add 4 to the sample size. So and then you do a walled. What you get then is I think that it protects you from getting negative numbers in your confidence interval. At any rate, so most stats courses are going to be just using the approximate confidence interval. If you're using a normal distribution to approximate it, that's what you're doing. Let's look at this. So this is if you're using data, and this just pulls in the data from up above. If I want to instead enter summary stats, I can enter whatever I want. So let's say at another sample site, I found, let's say, 4 sea turtles that were underweight out of a sample size of 62. That's all you have to enter, and it gets you your confidence interval. If you want to change the confidence level, you go up here, you change it to 0.92 or whatever, and everything gets updated for you. Very easy. Couldn't get easier. Now let's look at testing the proportion. I'm going to go and expand the test for proportion, and I want to say, let's see that that the in the wild, let's say that only 1% of sea turtles have a weight less than 20 kilograms, adult sea turtles. Oops, sorry, I'm building a hypothesis test, and I'm gonna just set this up. Consider a success less than 20. So what I'm doing is I want to see whether this area of ocean that I've looked at is significantly different than the species average. And so significantly different, I'm going to put P not equal to for my alternative hypothesis. So the null hypothesis is that the population proportion in this area of ocean is 0.01. The alternative is that it's not equal to 0.01. So, and then it just pulls together the data, gives me a Z statistic. It tells me a rejection region. Oh, I'm sorry. You know what? My significance level, it's set at 0.05. So that's there. You can change it if you need to. I'm using 0.05 for this. And then it looks like the approximate normal p-value is 0.039. So if I was using the normal approximation, I would reject the null hypothesis. I'm actually low enough. I guess that what I have here is higher than 0.01. It looks like there's more little sea turtles in this, significantly more. Of course, if you use the exact binomial p-value, that's not a rejection. So the difference, it depends on whether you're using the exact. You're going to get different conclusions for extremely low and extremely high sample proportions. That happens. Incidentally, if I go and look, this is the image that it gives you for the rejection region, shaded in blue. So the Z star is the critical Z value, and the Z that's marked right there. My Z value lives nicely in the rejection region. So the conclusion would be like to reject the null hypothesis. There is statistically significant evidence, or it's statistically significant, different than 1%. So anyway, this is sample inference for proportions using data or using summary stats. So summary stats, you just click there and you'd enter your summary stats. Instead of going from data, you just enter this number of successes and the sample size. Let's go to two samples. So if you click on quantitative 2 sample, that takes you to the other page, which I have open here. So let's say let's say I am doing the same thing. I'm surveying 2 areas of the ocean, these sea turtles. I'll call this CA, and this is CB. So this is my 2 areas of ocean. I want to see if the proportion of sea turtles weighing less than 20 kilograms is different. So to estimate the difference of proportions, just click on the difference of proportions tab. I'm going to set a success, again, less than 20, and we'll just see what we get for our results. So we're told that we have 2 out of 52 in ocean in CA, and 5 out of 52 in ocean or in CB. So there are different proportions. We want to see if it's significantly different. Well, this calculates a 95% confidence interval for the difference in proportions, PA minus PB, and the approximate interval is, using a normal distribution, it goes from negative 0.15 up to 0.038. In fact, that's not a significant difference, because in order for me to say that I am 95% confident that in one of the seas that the proportion of pipsqueak sea turtles is higher than the other one, I would need this confidence interval to not include 0. But it goes from the negative numbers to the positive numbers, so it actually is going to not be a conclusive confidence interval. If I did enter summary stats, you do the same thing by just entering the number of successes and failures in each of the two. And then it'll calculate the difference for you. And then to do a hypothesis test on the difference of proportions, I can say, okay, well, let's see if you can see if I want to set success to be proportion or a weight less than 20. This is going to test. Let's say somebody says to me, in CB the sea turtles are smaller. I say, I want to check if that's really true. I'm going to check if the proportion of small sea turtles in CA is lower than the proportion in CB. So that's equivalent to saying PA minus PB is less than 0. I can actually put in a different number here if I wanted to see if it's 1 percentage point lower or 2 percentage points lower. Anyway, we can see what we get. So it gives us sample proportions just like we had before, and it gives us a z-statistic for our test and a rejection region, and it tells us that we have a p-value of 0.12. So at a significance level of 0.05, I wouldn't reject that null hypothesis. There's not enough evidence to say that indeed the sea turtles are significantly smaller. The proportion of small sea turtles is significantly larger in CB rather than CA. And then you can do the same thing by entering summary stats. It's straightforward. And then I guess the last thing that I would point out is there's a tool, a sample size calculator, which is useful for inference of proportions. The sample size calculator is very straightforward. For proportion sample size, if I have a target margin of error and I have some estimate of the proportion, if I say, let's say, for example, that I suspect that, let's change it from sea turtles to something else. Let's say that that about, let's say, I think that about 15%, about 15% of German shepherds have green eyes. And I want to come up with a good confidence interval for that. I think it's about 15%. So, and I want a margin of error of 0.02. Well, there we go. It tells me I need to sample 1,225 German shepherds. If I don't have any sort of estimate of the sample of the proportion beforehand, just leave it blank. That's the largest sample size we would ever need in order to achieve a margin of error of 0.02. The margin of error might be way smaller, but this is the worst case scenario. If you're not sure what the proportion is, just leave it blank. It calculates the sample size you need for you. And that is that. It's assuming the normal approximation. So it uses for a walled interval, if you want to be technical about it. Anyway, that's an overview of proportion inference in StatPowers.